Hello everyone. In the previous video, we have seen one very important theorem that any permutation can be written as product of disjoint cycles. And we have also seen one property of transposition that any R cycle can be written as product of R minus 1 transpositions. So from these two theorems, what do we get? Every permutation in Sn can be written as product of disjoint cycles, and every cycle can be written as product of transpositions. So eventually, thus every permutation, thus every permutation in Sn can be written as product of transpositions. Product of transpositions. For example, if you consider the cycle sigma is equal to the cycle 1 mapping to 4, sorry, the permutation 1 mapping to 4, 2 mapping to 3, 3 mapping to 2, 4 mapping to 5, 5 mapping to 1, 6 mapping to 8, 7 is fixed, 8 mapping to 6 in S8. Sigma is a permutation in S8. So how can we observe this remark from the sigma? Every permutation can be written as product of disjoint cycles. So write sigma as product of disjoint cycles first. So you choose any, you start with any element of the set 1, 2, 3, 4, 5, 6, 7, 8. Usually you start with 1, so let us start with 1. 1 maps to 4, 4 maps to 5, 5 again goes back to 1. So close the cycle here and take any element which is not there in this cycle. So start with 2, 2 maps to 3, 3 maps to again 2. So close the cycle here. Then take an element which is not there in these two cycles. So let me take 6, 6 mapping to 8, 8 is mapping to 6. So close the cycle here. And then take an element which is not there in these three cycles, which is 7. So 7 maps to 7. So you get a one cycle. If you don't write this cycle, then also it is okay. It is understood that 7 is mapping to itself. So we have written sigma as product of disjoint cycles. Now we see the remark that every cycle can be written as product of transpositions. So you can write this cycle 1, 4, 5 as a transposition 1, 5, 1, 4. Product of two transpositions. This is already a transposition 2, 3. This is already a transposition 6, 8. So what do we have? That every permutation in Sn can be written as product of transpositions. Now this remark is important to define even and odd permutations. So let us see the definition of even permutation and odd permutation. So the definition of even and odd permutation. So first let us write the definition of even permutation. If a permutation in Sn, if a permutation in Sn can be written as for permutation in Sn can be written as product of even number of transpositions. Even number of transpositions. In the previous remark only we have seen that every permutation can be written as product of transpositions. If there are even number of transpositions in that permutation, then such permutation is called, it is called as even permutation. Then such permutation is called even permutation. And if a permutation in Sn, and if a permutation in Sn can be written as product of odd number of transpositions. If a permutation can be written as product of odd number of transpositions, then it is called as odd permutation. Then it is called as odd permutation. So to get clear idea about the definition of even and odd permutation, let us consider one example. So let me rub this definition and let us see with the help of an example then that how permutation is called even and when it is called odd. So let me take two examples from S7. In S7, check if the following permutations are even or odd. So let us see the first permutation alpha, which is given by 1 mapping to 5, 2 mapping to 7, 3 mapping to 6, 4 goes to itself, 5 goes to 3, 6 mapping to 1, 7 mapping to 2. So we have to find whether this permutation is even or odd. So you have to count the number of transpositions in this permutation. So first write this permutation as product of disjoint cycles. So let us start with 1. 1 goes to 5, 5 goes to 3, 3 is going to 6, 6 is again going back to 1. So we'll close the cycle here. Take an element which is not there in this cycle. Let us start with 2. 2 is mapping to 7, 7 is mapping to 2. So close this cycle here. Then take an element which is not there in these two cycles, that is 4. 4 is mapping to itself. So we have exhausted all the elements from the set 1, 2, 3, 4, 5, 6, 7. So this is our permutation alpha in cyclic notation. Now you write it as a product of transposition. So this cycle can be written as, this cycle is of length 1, 2, 1, 5, 3, 6, length 4. So you can write it as product of 3 transpositions as 1, 6, 1, 3, 1, 5. Then you have the transposition 2, 7. And you can ignore the one cycle 4. So how many transpositions are there? There are 4 transpositions. There are 4 transpositions in alpha. Hence, so therefore, alpha is an even permutation. So alpha is an even permutation. Let us see one more example. Consider the second example from S7 only. The second permutation tau is 1 mapping to 1, 2 mapping to 3, 3 mapping to 6, 4 mapping to 7, 5 is mapping to 5, 6 is mapping to 2, 7 is mapping to 4. So we have to count the number of transpositions in tau. First write tau as product of disjoint cycles. So here you observe that 1 is mapping to itself, so you will get first a 1 cycle, then 2 is mapping to 3, 3 is mapping to 6, 6 is again going back to 2, so close the cycle. Consider an element which is not there in these two cycles, start with 4, 4 is mapping to 7, 7 is mapping to 4 back again, then consider an element which is not there in these three cycles, which is 5, and you see that 5 is mapping to itself. We have considered all the elements 1, 2, 3, 4, 5, 6, 7. So this is your permutation tau and cyclic mutation. Now we will write tau as product of transpositions. So it is a one cycle, we'll ignore it. This can be written as, it is a 3 cycle, r minus 1 transpositions you can write. So you can write it as product of 2 transpositions, 2, 6, 2, 3. And this is already a transposition 4, 7. So therefore there are 3 transpositions in tau. Hence, tau is an odd permutation. So I hope you have understood the definitions of even and odd permutation. One important remark about cycles. So remark, every even cycle means a cycle whose length is an even number. Every even cycle is an odd permutation. Every even cycle is an odd permutation, because every cycle can be written as, every r cycle can be written as product of r minus 1 permutation. So even if you subtract 1 from an even number, you will get an odd number. Okay, so every even cycle is an odd permutation, and every odd cycle means a cycle of length, which is an odd number. Every odd cycle is an even permutation. So every 3 cycle will be an even permutation. For example, cycle sigma, say 2, 5, 8 in S8. It is a 3 cycle, but you can write sigma as product of 2 transpositions, 2, 8, 2, 5. So there are 2 transpositions in sigma, therefore it is even permutation. Odd length cycle but even permutation. Say alpha, consider any other cycle in S8, say 1, 6, 3, 7. Now you can write it as product of 3 transpositions, 1, 7, 1, 3, 1, 6. As there are 3 transpositions, so therefore it is an odd permutation. So every even cycle is odd permutation and every odd cycle is even permutation.